Hello, this is Nobuhiro Yanai from Kyushu University, Japan. So this is my great honor to receive the APA prize for young scientists. So I'd like to appreciate all the committee members of APA. And also I want to greatly thank to all the organizers of this APC 2021 for giving me this such a great opportunity to deliver this award talk. So of course, I want to thank all my coworkers and the collaborators for making all this work possible. And also, I'd appreciate all the funding resources for allow us to conduct research. Okay, so here shows our research interest. So we are interested in the photoexcited triple state of the molecules. It's because, as you know, that the triple state has very interesting characteristics, such as a millisecond scale of long lifetime, and also it can produce the polarized spins at room temperature. So we are focusing on the functions only achievable with the molecular triplets. So we call it as the functional chemistry of the triple state. So among functions of the triple state, we are currently focusing on the two functions. One is photon upconversion, another one is hyperpolarization. So indeed, our title includes both of them. That's the material chemistry of photon upconversion and triple dynamic nuclear polarization. However, because of the time limitation, today in this talk, I want to focus on this upconversion. So upconversion is a process that converts the longer wavelength light to the shorter wavelength light. So in terms of energy, it's from the lower energy to higher energy. So, it's actually the applications of upconversion can be very wide ranges from the energy to biology. For energy applications, you can harvest the unused sub-band gap photons by using upconversion, and you can enhance the efficiency of all the solar powered devices. And as you know, the near-field light have a good transparency in biological tissues, so upconversion can be very useful as an internal light source for biological applications. So there are several upconversion mechanisms, such as the two-photon absorption and the multi-step excitation of lanthanides. But unfortunately, they require very strong excitation lights at over watt per square centimeter. So eventually at the solar irradiance, so the quantum yield becomes very low. So instead, the people have recently interested in the triple annihilation TTA-based upconversion because it works at a low irradiance, and also upconversion efficiency can be high, typically up to 40% if you set 100% as a maximum. So here shows the mechanism of the triple annihilation TTA-based upconversion. So you need a combination of the donor and acceptor, triplet donor and triplet acceptor. So donor first absorbs the light, and then goes the intersystem crossing to become a triplet state. And this triplet state transfers energy to the acceptor through the dexter energy transfer TET process. And these sensitized acceptor triplets again meet to undergo TTA to produce one higher energy S1, and one goes back to the ground state. And then you can get upconverted emission from this higher energy single state. So key here is that you need to do the 2 times of the dexter energy transfer process, and 1 time of the dexter energy transfer TTA process. So to achieve these energy transfer processes, so people have usually used the molecular diffusion in solution or polymer. So you need a mixture of donor and acceptor, and donors of the light transfer energy to the acceptor, and these sensitized acceptor triplets again meet to show the upconversion. However, we have been proposing to shift from this molecular diffusion to the energy migration in condensed system. So here, a donor is doped in dense acceptor assembly. And qubit exciton diffuse in this assembly to show the upconversion. But why we need that? So because we see several severe issues in this molecular diffusion upconversion. For example, you need volatile solvents, and the diffusion is quite limited in solid systems, and you need to strictly remove oxygen to avoid the quenching of this turbid. So that we have proposed to shift from this diffusion to the exciton diffusion, because now you need no solvents, and also you can achieve the upconversion at low excitation intensity if the qubit migrate fast enough. And also it should be compatible with oxygen barrier materials. So with this strategy, we have systematically studied many different molecular assembly systems, and many of them are the first example showing the upconversion. So because of time limitation, I want to give you only a few examples to give you some idea about this energy migration-based upconversion. So here is the example of upconversion in air-saturated water. So we designed this type of the amphiphilic acceptor molecule, having the acceptor and also the hydrophobic acceptor and hydrophilic terminal groups. So this acceptor self-assemble in water together with counter-anion fatty acid and also the small amount of donor. This supramolecular assembly shows a very nice upconversion even in air-saturated water. So thanks to the dense molecular assembly structure, the oxygen blocking efficiency can be very efficient, 80%, so that we can achieve the high upconversion efficiency of 14%, even in such a air-saturated condition. And we found that this strategy is quite general, so we can also achieve the upconverting hydrogel in air. So by just combining this biopolymer gelatin and donor and acceptor in water. And upconversion efficiency can be very high, close to 14% in air. Okay, so now I want to switch to the topic to the wavelengths problem. So near-infrared to the visible upconversion is very useful for the energy and the biological applications. However, it has been very difficult. So why? Because the problem is in donor. So during the intersystem crossing from S1 to T1, donor lose a lot of energy, like about 100 of millielectron volt. So that this is actually a very severe problem in the near-infrared region, so that you can find acceptor with even lower turbid energy level, but it's already too low to come back to the visible range with a good efficiency. So we try to solve this issue by developing the new mechanism. So we employ this ST absorption, that's the direct transition from the ground state to the turbid state. So of course, this is spin forbidden process, but some metal complex like osmium complex showed a nice ST absorption in near-infrared range thanks to the heavy metal effect of the osmium. So this ST absorption is very useful because you can now skip this intersystem crossing, so you can avoid the energy loss. So you can sensitize the qubit by using the near-infrared light. So we combine with this osmium complex with the acceptor lubrine. So we doped osmium complex in the lubrine nanoparticle and embedded in the oxygen blocking PVA, and we achieved the near-infrared to the visible upconversion by using such an invisible near-infrared light over 900 nanometer. So this is actually the first example of purely molecular system efficiently upconverting near-infrared over 900 nanometer light. But actually, the upconversion efficiency was moderate at that time, 0.43%. But later, we succeeded to improve the efficiency to about 4% by just adding the third component collector, DBP, small amount of collector. So why the upconversion efficiency was improved? There are several reasons. So first, actually this DBP is kind of isolated in the solid. So it shows the improved fluorescence contaminant. And second, this back energy transfer from this collector to donor is largely avoided because of the large separation, large distance between this DBP and donor. And third, this energy collection process is very selective against the back energy transfer because of the larger flat rate constant from this lubricant to the DBP than this to donor. And the last, actually it's related to singlet fission. So the lubricant S1 energy level is about twice of this triplet energy level. So both of TTA and singlet fission can happen. So actually, people, including us, assume that this energy collection can compete with singlet fission. But recently, we found it's not true, it's not correct. So by the collaboration with Jenny Crack group in University of Sheffield, we found that the addition of this collector DBP do not affect the singlet fission dynamics. It happens in the picosecond time scale. And after singlet fission, DBP singlet was formed. So what happens? So actually this singlet fission is about happens in 10 picoseconds. So it's too fast. So the thread is about 50 picoseconds. So it cannot compete with singlet fission. But after singlet fission, by closely looking at dynamics, we found that triplet hopping and spin evolution to produce free triplet, this process is slow. So more than 100 picoseconds. So this energy collection process can compete with this slow triplet pair separation process, so that eventually it can harvest the energy to this DBP and can improve the efficiency of the upconversion by avoiding the loss of the triplets after triplet separation. Okay, so we have the now much better understanding. And actually by using this improved efficiency of the upconversion, we could combine with the perovskite solar cell. This is collaboration work with Yabin Chi group in OIST. So we showed for the first time that near-infrared sensitivity can be added by combining with this molecular TTA upconversion system. Okay, so ST absorption is good because you can sensitize by the near-infrared excitation. However, it's not perfect because actually triplet lifetime of this ST absorption is very short, usually less than microsecond and nanosecond scale because of the heavy metal effect. So to solve this issue, we took the strategy of covariant conjugation of this donor and acceptor. So immediately after ST absorption, the triplet energy is transferred to this acceptor unit with much longer triplet lifetime. So triplet energy can be pooled. So with this strategy, we successfully elongate the triplet lifetime over 100 times. So now the ST absorption and long triplet lifetime becomes possible. So we use this donor acceptor conjugate and combined with this free acceptor in solution, we achieved a very nice near-infrared, the blue upconversion. Actually, we achieved this near-infrared to blue upconversion for the first time. And we use it for the biological applications. So people have reported the beautiful examples of the biological applications, such as bioimaging and drug release using the molecular conversion, but there are no example of optogenetics. And you know, the optogenetics is very powerful tool to control the and understand the functions of the brains. However, the problem is that you need a blue light, so that you need to open the mouth of the brain and insert optical fiber. And even if you do so, you can excite only at the surface of the brain because of the poor penetration of the blue light. So, but if you use the near-infrared, the blue up conversion, you can excite from outside the brain, and also you can excite the deep tissue of the brain. So by collaboration with the Ajioka group at Tokyo Medical Dentist University and the Sato group at the University of Tokyo, we demonstrated the first example of the optogenetics by the molecular upconversion. So we embedded our donor acceptor conjugate and free acceptor into the biocompatible hydrogel, and we combined it with the blue light sensitive genetically engineered neuron. So by absorbing the blue light, so this neuron can express some target genes, and we chose the spine formation of the hippocampus neuron because it's the beginning process of learning and memory. So we excite the near-infrared and then produce the blue light. And actually, we observed a very nice spine formation in the hippocampus neural cell. So we could initiate the learning and the memory process by using the upconversion. So this is the in vitro experiment. So now we are trying to extend it to the in vivo application. So the last topic of today is the visible to UV upconversion. So this visible to UV upconversion is very useful for the photocatalytic and the photosynthesis reactions. However, unfortunately, the efficiency was low. It's lower than 10%, often much lower, less than 1%. And you need a very high excitation intensity over watt per square centimeter, much stronger than sunlight. So after many trials, we eventually recently developed a very good combination of the donor and acceptor. So a donor is the iridium complex. It shows a very strong excited absorption in the visible range. And also, very importantly, it has much less absorption in the UV range. That's very useful to avoid the back energy transfer or reabsorption of the upconverted emission. And we found that this acceptor tips naphthalene, we call. These have the very low triplet energy that can be sensitized by this iridium complex, coumaline complex, and it shows a strong UV emission. So with this the combination of donor and acceptor, we achieved a very nice visible to UV upconversion with the highest efficiency of the 20%. Actually, this is twice higher than the previous record of about 10%. And more importantly, we achieved a very low threshold excitation intensity, even lower than 1 sun. So actually, we could observe the nice UV emission under the excitation of the solar simulator, 1 sun. And actually, we could even use the much weaker light, like room LED, to produce the UV upconverted emission. Okay, so at last, I want to share the future challenges in this field. So our dream is a future where the upconversion is all around us. So we want to contribute to a wide range of fields involving light by using upconversion. Towards such a goal, we need to develop the basic science, that is the ultimate upconversion materials and devices, such as we need a rational molecular design to achieve 100% of upconversion efficiency, and we need a material device for the high upconversion efficiency at the 1 sun, and we need air stable upconversion materials for real-world applications. Okay, and thank you everyone for your attention. And also, again, I want to greatly appreciate this award from APA. Thank you very much.